we have our first speaker. This is Piotr Tarasiewicz from NVIDIA, and he will tell us something about Dynamo, which is a distributed data center scale distributed inference serving framework. Perfect. So the floor is yours.
Hello, everyone. Let me tell you a few words about Dynamo. This is a new framework that NVIDIA released at GTC like 3 or 4 weeks ago. But it's completely open source. I will drop links at the end of the presentation. Let's get started. So quickly on the agenda, I will start with an overview of what is Dynamo, and then I will go over a few features that Dynamo enables you to do, like smart routing, KV cache offloading, and disaggregated serving. And then I will give you a quick start on how you can use it, basically. Okay, so Dynamo overview. So what were the goals? So we wanted to build a inference framework with mainly large language models in mind. And we had a few assumptions that we wanted to have. So like, first of all, it was Python API. So even though it's built in mainly in Rust, the API is written in Python, and it's Pythonic to like the we gave it our best effort to keep it Pythonic. So if you're a user, you don't have to write anything in Rust, you can just use Python. We wanted to provide high performance components for LLM deployments. So Dynamo is not restricted to LLMs, but the components we provide are mainly dedicated to LLMs, but you can write your own components. It had to be easy to use and also easy to extend, and DL framework agnostic. So we provide reference implementations for TensorRT LLM and VLLM, but if you want to use SGLang or native PyTorch or Mistral or anything else, Mistral RS, anything else, or Llama, Llama CPP, whatever you want, you can just extend Dynamo and use it. And also we wanted to support Kubernetes deployment. Okay, so I will quickly go over the current architecture. So these are the main components that we provide. So first of all, there's API server. So the user will send the request to the API server, and it is compatible with OpenAI API. So any request you are sending to OpenAI or to Claude or Hugging Face, TGI, and so on is also compatible with Dynamo. Then we have smart router component that will decide to which worker it will send the request from the user. Then we have disaggregated serving. I will talk a little bit more about that because I assume not everyone is very much involved with LLMs. And also we have like side components like planner that can scale up and down workers. We have the KV cache manager, event plane for reporting metrics, and then some low-level libraries that allow us to move the KV cache between the components. So I will start with briefly giving an introduction to what is exactly the KV cache, because it's like behind most of the Dynamo components. It's all about KV cache movement, KV cache offloading, and so on. So I assume you have some basic idea of how LLM works. But like all you need to know is that they predict the next token, right? So the input sequence is encoded as tokens. So in this graphic, each word is a token. It's not necessarily true, but it doesn't matter for this example. So each word here is a token, and then LLM will predict the next token, concatenate this token as an input, and then predict the next one, the next one, and the next one. And that's all the model does. But then for each token in the input sequence, model actually has to calculate key and value vectors, maybe multiple vectors for if there are many attention heads. And those key and values, so we call them KVs, keys and values, only depend on given token and all the tokens that precede it, right? So for example, key and values for low only depends on recite the first law and not on whatever happens next in the sequence, right? So what does it mean? It means we can actually store the KVs and reuse them and not recompute them again, and again. So when we want to compute the next token, we don't have to recompute all the KVs because they won't change, because whatever was preceding those tokens doesn't change when we generate next tokens. So and we store them in KV cache. And it's really important concept because without that, you can imagine that, for example, if the length of the sequence is n, you would compute each of the n tokens n times, right? So it would grow quadratically the number of keys and values you have to compute. And with caching, it's growing linearly, number of KVs. So this is the basic use case, is generating the next token in the sequence. So that's what all of the LLM framework will support. It will, underneath it will use KV cache when generating a sequence. But there are more use cases. For example, we can store KVs for system prompt. So system prompt is something that the LLM serving platform will concatenate in the beginning of each request, right? So for example, Anthropic publish what they're actually using as a system prompt to their Claude models. So if you send a request to Claude, they will always start the request with the assistance Claude created by Anthropic, and so on and so on and so on. This is like hundreds of lines of text, and then at the end they will actually concatenate your request. So this prompt will be the same for every request. So it doesn't make sense to recompute the KVs every time, right? So that's another use case for the KV cache. And also another one is simply a multi-turn chat, right? So if you chat and let's say you stop chatting with ChatGPT for, I don't know, 5 minutes, but then you come back, ask the next question, it can either use cached KVs for your previous conversation, or it will have to recompute it all over again. And computation is expensive, right? So for example, for Llama 3.1, for each token, there's 320 kilobytes worth of KVs, right? But if you cache them, you sacrifice memory, but reading from memory, especially from VRAM on GPU, is much, much faster than recomputing, especially for large models. So this is what we mean by smart routing, is basically routing each request to a worker with the best prefix match, so that we can reuse as many KVs as possible, right? So we can imagine that user was chatting with a model on node A, and then he comes back 5 minutes later, sends us another request. We have like hundreds of nodes, but we want to route this request to the same node because the KVs are already there and model won't have to recompute them. So that's the idea behind KV cache routing. So that's why the first component behind the API server is the router. So we want to track the state of KV cache of each worker and then route to the best one. And there are two main factors in the cost function. So one is where is the best KV cache match, so on which worker will be able to use the most KVs, but also we have to take into consideration the load. If the worker is busy and cannot take more requests at the time, we have to recompute, not to wait, I don't know, a few seconds before we actually send an answer. So what are the results? When you turn on the smart routing for Dynamo, this is a quick test with 100K requests to Llama 70B models. We were using 2 nodes of H100, and the average input sequence length was 4,800 output sequence length. And the ideal KV cache hit would be around 60%. So between the requests, 60% of inputs were cached in, could have been cached from previous requests. So if you do random routing compared with Dynamo, for time to first token metrics, in this specific use case, it brought 3 times it resulted in 3 times faster time to first token and 2 times faster average request latency. So request latency won't be improved as much because you still have to generate the tokens, but the time to the first token, which is the most expensive one, because normally you have to calculate KVs for all of the tokens in the input sequence. Now you reuse them, so time to first token improved vastly. So that's the first component. But as I mentioned, there's 320 kilobytes per each token for Llama 70B. For Llama 405B, it will be even more, around 800 kilobytes. So if we have a single node that is able to generate 1,000 tokens per second, then the KV cache will grow 320 megabytes each second and 19 gigabytes each minute, right? And we can imagine that our GPU, even if it's like top of the line B200, it will have like 140 gigabytes worth of VRAM, and then most of that will be used by the model itself. So it's like after, 4 minutes, you will have to evict some KVs, right? You have to get rid of some KVs to make room for the new ones. And that's why we introduce the concept of like implementation of KV cache offloading. The concept is not new. So that you can offload KVs from GPU memory first to host memory. So you can offload KVs to DRAM, and then if required, you can simply, instead of recomputing, you will read from DRAM. And this bandwidth, it has a very large bandwidth, like hundreds gigabytes per second. But then if your DRAM is already full, you can also use local SSD, which is can be much bigger, but the bandwidth will be smaller. And if that's not enough, you can actually use some shared network storage like S3 on Amazon, for example, right? So you can imagine that the user, if the user is constantly chatting with the model, you will be using GPU memory. If the user will leave the conversation for 30 seconds or 1 minute, you will offload to host memory. But then if the user will close the session, you can store KVs on S3, and if the user will come back the next day, you can read KVs from S3, right? So that's why we use hierarchical KV cache. So if you go down, the bandwidth is smaller, so it will take longer to load KVs, but we have more space. So that's another component that Dynamo has. Okay, so we also did some similar experiments. So here we tested the multi-turn chat, and we always use the GPU prefix caching, but one with host offloading and one without. So we can see that if we use only the GPU for the first few turns, so the first few chats, messages that the user will send to the model, we will be faster because GPU read from GPU memory will be faster. But then we will quickly we won't have the memory available, so we'll have to evict some KVs from the GPU memory, and then we'll have to recompute them. So in that case, offloading after a few turns will be faster and faster, and the time to first token won't grow as quickly because we'll be able to reuse more KVs with the offloading. So that's another idea, and it's simply all about making things faster but also cheaper, right? So the same GPU will be able to serve more users because it will simply reuse previous calculations. Okay, so that's Smart Router and the KV Cache Manager. So then another component of Dynamo is the disaggregated serving. So I will talk a bit about that. So you can imagine that there are two distinct parts of LLM inference, right? So you send a request to ChatGPT. So let's say it has, 100 words, right? So first, the LLM will have to compute KVs for all of the tokens you've sent to it, right? And then it will start generating tokens one by one and calculating, reusing previous KVs and generating token after token after token. So you can imagine that the first part is very computational heavy because we can calculate all of the KVs at the same time. So it can be 100 tokens, but the input sequence can be, with Llama 4 that was released last week, it's up to 10 million tokens of input sequence length, right? So it can be very computational heavy. We calculate all of the KVs for all of the tokens in this at the same time. But then when we generate token after token after token, there's not much computation we can do, right? So we only generate KVs for a single token every time because we cannot generate. There are techniques for that, but like in general, we can't generate more than one token at a time with the same model. There are like techniques like speculative decoding, but for a single model, we cannot generate more than one token at a time, right? So we move a lot of data, we load and offload a lot of model weights, activation, KVs, but we don't do too much computation. So we can, for example, increase the batch size to increase the computational load, but for a particular request, there's only so much computation we can do. So in the first part, we are usually compute bound. In the second part, so the time it takes to calculate the prefill, so that's what we call calculating KVs for all the input, is bounded by the time of the computations that happens on the GPU. And for decode, so for generating token after token after token, we are bounded by the speed of which we can load and offload memory from the GPU, right? So those are two very distinct parts, and usually, like most of the models, combine them together. So naively, for example, they will run decoding for, I know, 100 requests, but then a new request comes, and they will stop decoding and then run prefill for this, interrupt decoding, and then come back to decoding. Or they will try to overlap and interleave the two, but they will use the same engine for both prefill and decode. So what is disaggregated, the idea behind disaggregation is very simple. So let's use separate engines for those two separate tasks, right? Let's use one engine for doing prefill and another engine for doing decode. And we can scale them independently, but also we can optimize them independently. So because those tasks are very different, we want to optimize them differently. And that's the very simple idea behind disaggregation. But what needs to be done is when prefill computes all of the KVs for the inputs, the KV cache has to be transferred to the decode, right? So that's the added complexity of disaggregation, and that's what Dynamo does for you, basically, the KV cache movement. So here are also some results of our experimentations. So this is what we call Pareto charts. So on the x-axis, we plot number of tokens per second that we generate for particular requests, right? So this is from the user perspective. So that's why we call it tokens per second per user. So if you are a user, how many tokens per second are you getting? And on the y-axis, we plot tokens per second per GPU. So for all of the users, the particular node is serving, how many total tokens are we producing, right? Because we want to run with some batch size, right? So some GPU will serve 100 or 200 or 1,000 different users running with batch size of 1,000, right? So you can imagine that this axis is really an inverse of latency, and this axis is basically a throughput, right? And so the lowest latency, so we'll be somewhere over here, is when we only serve one user, right? So that's why when all of the computation can be dedicated to a single user. But then as we increase the number of concurrent users, so as we increase the batch size, the overall throughput will grow, but the latency will decrease, right? So that's what this chart is showing. And here on the orange, with the orange line, we show the baseline, which is basically your standard, in this case, VLM model that's not doing disaggregated serving. and then in blue is disaggregated serving with Dynamo. So for example, with a single node, we can see that, for example, at 40, let's say 50 tokens per second per user, so given the latency, we're able to improve throughput 30%. So the user won't be able to tell the difference. From the user perspective, the speed is the same, but you will be able to serve 30% more users with the same hardware, right? But if you move to 2 nodes and then enable more opportunities to differently optimize prefill and decode and to better balance between number of workers for the 2, we actually are able to increase the throughput 2 times without hitting the latency, right? So with the same latency, you are able to serve twice as many users on 2 nodes, right? And that's normalized to the number of GPUs. So this is also another way to make LLM inference cheaper, basically. Okay, so that's disaggregated serving. There are also some components I won't be talking too much about. So one is Planner, that is scaling the workers up and down. And I won't talk too much about it because this is still under development. And the other one is Nixel, which is new NVIDIA library, but it's kind of low-level library for data transfer between the nodes. So that's what we use to move KV cache between nodes or from GPU to host memory and so on. But then I want to tell you about how you can actually use Dynamo. So installation and so on you will find on the GitHub repo. But to actually serve the model, when you prepare configuration, is simply running Dynamo serve, and then you specify what do you want to serve, so your serving file, and then the configuration file. So what's the content of the files? So the graph is simply your computational graph that the request will follow, right? So if we come back here, we have API server, which is a front end, and then from there, their request will go to the router. From there, it will go to decode worker, and decode worker will ask prefill worker to do the prefill, so compute KV, initial KVs, right? So we can imagine that this is a graph. So router is linked to the front end, the decode worker is linked to the router, and then prefill is linked to decode, right? So this is exactly what you specify here, right? You initialize front end, then linked another, this is processor, that's not on the previous chart, but this is simply pre and post processing, right? So tokenizer, encoding, decoding the request, then we link router, then we link decode worker and the prefill worker, right? So then if you say, I want to serve the front-end components, and it has linked all the other components, it will automatically also serve all of like your full graph, basically, right? So you only has to specify, I want to deploy front-end, and everything that's required for front-end to actually work will be deployed. And then configuration file is simply a YAML with some arguments for each of the components. So for example, for the front-end, we want to specify what's the served model name and at which port are we serving, and the specific endpoint, right? So for the VLM worker, there are some VLM specific stuff like maximum model length or model checkpoint or enabling conditional disaggregation and so on, right? So this is like your VLM and some Dynamo arguments. So for example, for Dynamo arguments, we can specify the number of workers. So this would be number of decode workers, and then resources we want to assign to each of the worker, because this can work locally, but the same files will be used to deployment on Kubernetes. So then finally, I want to tell you briefly about how you can actually add new components. So this is an example of a router component. So to build new component, as you can see, we do that all in Python. So we just need to decorate some class with a service and enable Dynamo, right? And that's pretty much it. And then we can specify some resources that will be assigned to that service. And then we can do some initialization, right? So all of the components have access to Dynamo context. And through that context, they can communicate with other components. So for example, a router wants to communicate with VLM workers to receive some KV cache events, to keep track of KV state of each worker. So this all happens through Dynamo context. And then you can create Dynamo endpoints. So then when you run the components, it will create an endpoint, so you can send a request to it and receive back some response. So for example, in the case of the router, we will receive, we will send request to the router and get back the ID of the worker we need to route the work to. Right. So that's quite straightforward. And basically all of the components you've seen on the previous graph here, except for the front end, which is written purely in Rust for performance, basically for handling thousands and hundreds of thousands of concurrent users. But the router, the decode prefill worker, the KV cache manager, that's all written in Python and simply using the Dynamo runtime that's written in Rust. Yeah, and as I mentioned, this is all released under open source Apache 2.0 license, so we are really welcome any contributions. We already, over the last few weeks, accepted, I believe, over 10 PRs from outside contributors. So please check out star if you want, and like this QR code will direct you directly to the Dynamo repo. And that's pretty much it for me. Thank you.
Thanks very much. And are there any questions? Any questions about Dynamo? Okay.
So thanks for the presentation, first of all. And I wanted to ask about, so you mainly told us how you increase the throughput, but what about the latency? Are you also working on decreasing the latency?
In principle, the answer would be not really, because this will also be highly dependent on the underlying framework, right? So Dynamo will use like whatever you choose. So like we, as I mentioned, we provide workers for VLM and TRTLM, and really the minimizing the latency is requires work in the LLM engines, right? So optimizing specific kernels, schedulers to reduce overhead. So there's not much we can do on the Dynamo level. So for Dynamo, the goal is to like basically doing all of that. We know that we will add some overhead compared to if you just run on bare metal your VLM, right? So like all what we want to optimize is to minimize the latency overhead we are adding, but there's not much we can do with the, let's say, TRTLM or VLM latency. So that's work that's being done in the framework themselves, basically.
Thanks for the presentation. You talked about speculative decoding for a second. Can you build the components in Dynamo for speculating decoding? How would that work in here? Is it supported?
I mean, that's not, so that's supported. Like there are no components currently that runs speculative decoding or multi-token prediction in general. And there's like a bit of a fine line of what's integrated inside the worker, so inside, let's say, VLM, and what's integrated on Dynamo level. But in principle, the endpoint API is really in like some input, some output, right? So there's like certainly speculative decoding could be supported on the Dynamo level, but I don't think there's been any work on that at the moment, to be honest. So like that's one of the things that we actually welcome contribution to. So Mm-hmm. Yeah, exactly. And actually, like disaggregated serving on the decoding side. Let me. Yeah, so on the decoding side, since we are memory bound, we have usually some free flops that we could use for the smaller model to run speculative decoding. So we've run some like initial tests, and we see that's a promising direction, but like nothing's been actually implemented yet.
Any more questions? If there are none, thank you very. Oh, you have another one? Okay, yeah.
So any idea about mixture of experts? Is it something that could be optimized on a Dynamo level or only on a framework level?
I believe like most of the work here would happen on the framework level, but like for example, running disaggregation with mixture of experts, this is something we are actually currently working on for DeepSeek model. So yeah.
Okay, any more questions? Anywhere? If not, thank you very much, Piotr.
Thank you.